This is AP Precalculus. We're on notes for topic 1.2, rates of change. So let's dive in. The average rate of change. This word comes up over and over and over again. Anytime you see average rate of change, I said it in my last lesson, I'm saying it in this lesson over and over, it's just the slope between those 2 points. So again, when I'm defining the average rate of change, it's just the slope formula. The change in y's divided by the change in x's. So in general, to find any average rate of change for the function, you're going to first find the y values, because those are usually not given to you. So I'll say y values based on the x values that they give you. And then once you have the y values and you've already been provided the x values, then just find the slope. Let's see how that works. And again, there's a graphic representation of what's going on. It'll say, hey, I have an x-coordinate of -4. I have an x-coordinate of 0. What is the slope of the line? Well, you find the height. You find the y-coordinate. You find the y-coordinate. You say, okay, the change in y was 4. The change in x was also 4. Therefore, the slope here is going to be 1. All right, so jumping into example 1a, we have these x-coordinates, x-coordinate of -2, x-coordinate of -1 with this function, what's going on? So first we need to find the y values. That was step 1. So I'm going to say, okay, to find the y value of -2, you say f of -2. You're just plugging in -2 into each of these x's. So this, instead of negative x to the power of 3, it's going to be negative -2 to the power of 3. So negative, the quantity of -2 to the power of 3 plus 3 times that -2. And then I can simplify this a little bit. I can say, okay, anything to the power of 3, it doesn't change the sign in here. If I have even powers like powers of 2, it makes this always positive. If I have odd powers like powers of 3, it stays negative. So this is going to be a -8, and then a negative -8 is a positive 8. So I'm going to say positive 8. And then this is going to be -6 here, -6, and that's going to be 2. And then from here, I'm just making sure that makes sense to me. Yep, that sounds good. And then to find -1, I'm going to say f of -1. I'm going to plug it into the function again, negative the quantity of -1 quantity cubed plus 3 times -1. And that's going to be, again, this is -1 with another negative makes this a positive 1. So I'll say positive 1, and then -3 is a -2. So the question is, how much do you change for the x's? Again, I can use that old-fashioned formula, but I prefer doing it a little bit quicker. I say, okay, this is my change in x. My change in x in this case, to get from -2 to -1, I have to go up 1, so plus 1. And to get, for my y-coordinates, to get from 2 to -2, I have to go down, down 4. Just making sure my directions were correct. So I've gone right 1, down 4. So my general way of doing slope is a little bit different than this formula. You can use this one if you want. It works perfectly fine. But in general, I say that slope is equal to the change in y over the change in x. And I'm going to say that's a -4 for the change in y divided by a change of 1, and that is just evaluating to -4. All right, so I can box that. That's my final answer, and move on to the next one. All right, so again, I need to find my y values, so I have to plug in 1. When I plug in 1, I'm going to get 1 plus 1 all over 1 plus 6. This is going to be 2 over 7. And then I need to find h of 4. When I plug in 4, I'm going to get 4 plus 1 all over 4 plus 6. And this is going to be 5 over 10. And that can reduce all the way down to 1/2. All right, now we just need to find the change of x, change of y. So change of x, I'm clearly going right 3, so plus 3. This one is a bit harder to do, right? How do I do the change of y's because they're fractions? So this is where that old formula up here is going to be very helpful, and you have to make sure that we do it in the right order. Really what I was doing to get 3 was I was doing 4 minus 1. So you do the right minus the left. So I need to do the right minus the left in order to find the change from 2/7 to 1/2. So I'm going to say, what is 1/2 minus 2/7? And obviously we can't subtract straight through because our denominators are not like denominators. I need to get those like denominators, and I'm going to do that by multiplying by 7, multiplying by 7, multiplying by 2, multiplying by 2. All right, so now our new problem is going to be 7 over 14 minus 4 over 14. And that's equal to a 3 over 14. So this change, I can come down and erase this equal to sign, or this question mark, and I can say this is really a plus 3 over 14, which makes sense that I'm going positive because 2/7 is definitely smaller than 1/2, so I should be going positive. And then we get the even more difficult question, possibly more difficult question. How do I do the change of y divided by the change of x? Because again, that is my definition of slope. So I say slope is still equal to the change in y divided by the change in x. So my change of y is a positive 3/14. I don't have to do the positive. I can just say 3/14. 3/14. And then the change of x is a positive 3. So you'll probably be familiar with this. If you need to, and I should change the 3 into a blue 3 so that it makes sense with my color coding, shouldn't I? There we go. Whenever you have a nested fraction, a fraction within another fraction, you're going to keep it, change it, flip it. So I'm going to keep the 3/14. I'm going to change the division into a multiplication, so change into multiplication. And instead of multiplying by 3 right here, I'm going to flip 3, and it's going to become 1/3. So it's called a keep, change, flip. That's what happens when you have nested fractions. And this is kind of nice because, check this out. Oop, I didn't mean to do that. These 3's cross cancel, and you're left with just 1/14 for a final answer, which will then box. All right. So in example 2, the graph is shown below, and I set it up above. I should have said it again every single time. When it says find the average rate of change, I'm kind of crossing that out in my mind's eye, and I'm thinking of the word slope. This one down here is doing the same thing. Find the average rate of change, which I'm going to cross out, and I'm going to write the word slope. So whenever you have graphs, it's a lot easier. You just have to find the y-coordinates on the graph instead of having to plug it into some sort of algebra. So I say -1 is this point right here, positive 3 is this point up here, and the average rate of change is just that formula. So the change of y of the change of x. Graphically, it means that you're connecting them with a straight line and saying, what is the slope of that line? Well, I'm clearly going up 1, 2, 3, 4. So maybe I'll just do a dashed line for us. I'll say, okay, this is +4. +4, and this one is going right 4, so I can say another +4, and I can come back over to my generic slope formula, which I say is the change of y divided by the change in x. In this case, my change in y was a +4, my change of x was a +4, therefore my slope is just 1, which you probably could tell because it goes through, goes right 1, up 1, right 1, up 1, right 1, up 1 the entire way. Let's try another one. Oh, didn't mean to go backwards. In example 3, this is the first time that we're using the calculator in our class. So in my class, we use the Texas Instruments 84, the CE, the color edition. I don't have that on my iPad, so I have something that's very close. So I have something that's called Calculate 84. It's a little bit different for our interface, but I'd like to show us how to use a calculator. It's very, very similar. So we're trying to find the average rate of change. Again, every single time I'm seeing the word average rate of change, I'm crossing that off, and I'm changing that word for the word slope. So find the slope of the life expectancy, and these are the two dates we're using, 1850 and 2000. So 1850 and 2000, which means I'm not using any of those. So I have these are like the x coordinates, which are really the t coordinates, and those are they are a coordinates, but they're kind of like the y coordinates, right? So really what I'm doing is I'm coming back to my very basic definition of slope. Slope, again, is just the change in y over the change in x. In this case, it's really the change in capital A over the change in lowercase t. The change of A, again, I usually do the rightmost point divided by, or subtracting the leftmost point. So for my y coordinate, this is going to be 81.83 minus 46.10. Let's write that out. Come back over here and say 81.83 minus 46.10.10. And this is all going to be divided by 2,000 minus 1850. So a really common mistake that I have for students in all classes, from Algebra 1 all the way through AP Precalculus, is mixing these up. If you were to somehow change these two, the order, if you say 81.83 matches with 1850, 81.83 matches with 1850, you'll get the right answer, except it will be negative. It's like you multiplied the answer by a -1, and you'll kind of make sense. You're like, I got a weird negative slope, even though I should be going up from 46 to getting to 81.83. And then that's kind of your clue. You just have to think about the context of the problem. So I'm just going to type this into my calculator. Practice typing it in with me. So you should have parentheses because it's on top. Notice that the end parentheses have been entered for me on the normal Texas Instruments 84 or even the 83s. They shouldn't end the parentheses already. So I have 81.83 minus 46.10 0.1. You don't have to do the 0. Okay, that's the first set of parentheses. That is the numerator. I'm going to close my parentheses, and then I'm going to do divided by, and then start the next set of parentheses. This is the denominator. You can do this one in your head. It's 150, but you can say 2,000 minus 1850, and then end the parentheses, and that's how you should be doing your division. There we go. So I get exactly 0.2382. So it's time to talk about rounding in this class. Typically speaking, most AP questions will round to 3 decimal places. The only exception to that is when you're dealing with logarithms or something where you have to be super duper exact. But in general, as a general rule of thumb, round to 3 decimal places. I'm going to just round to 4 now because this one happened to be an exact value, and it's kind of nice to see that. So I'm not done with this question, and I mean, I'm done with the calculator. I'm not done with the question because notice that the question says, include units of measure. What is this measured in? So if it's the average rate of change, if it's the slope, then it's this unit divided by this unit. So it's the age in years per year of birth is our unit. So I'll say age, and instead of saying, I'm trying to figure out if I want to say, yeah, I'll say age per year, or maybe if you want to be more specific, you can say this is years, and then this is the birth year. What would be another way of saying this? You could say, I don't think you can make it any more specific than that because I don't want to get confused and do years divided by years and cancel out my units. I think I'm going to have to leave it as age per year. All right, so I should box my final answer, and then I can move on to my next question. All right, this is from last year. I need to erase all of this stuff so I can teach. Let's make sure that all of this stuff is gone as well. And now I can teach. Didn't realize that was still there. My apologies. So the instantaneous rate of change is this idea of having a slope at one point. So normally you've seen over here, we have slope at 2 points. We have a slope here, or these 2 points, and then we connect it with a line. And that's typically how we think about slopes in all of math. This is the first time where I'm going to be talking about the slope at 1 point. And the slope at 1 point has a special name. It's called the instantaneous rate of change. Sometimes if you're looking at a graph, it's called the tangent line because it touches only at 1 point as opposed to a secant line that touches at 2 points. But in general, we have to wait till calculus to be able to actually have the instantaneous rate of change. But if you just get really, really close to the same point, so let's go ahead and make up a story. Here's my graph, and maybe I have some weird curve like that. And I'm like, okay, I have these 2 points, and if I connect those 2 points with a straight line, okay, I mean, I try to connect with a straight line. Yeah, you can see, oh my God, I'm really bad at doing that. There we go. Yes, you get the slope. But what if this point was really, really close and I connect with a straight line? What if I could zoom into this graph really, really, really far and basically get these 2 points so close together that they look like they're 1 point? That's what we're going to do in AP Precalculus. So we can approximate that rate of change of the instantaneous rate of change if we take the points close enough. So we can say using the average rate of change, aka the slope, right? If you use the slope over small intervals. And that will turn it essentially into a 1 point slope as opposed to a 2 point slope. So let's go ahead and see an example of what that would look like. So notice that each of these are giving x coordinates, x coordinate of 1 and then 1.1, which are really, really close together. These are even more close together. These are even more close together. And this one is on the other side, right? This is kind of on the right side of 1. This is kind of on the left side of 1. I'm curious, before you even begin doing the math with your calculators, we will be bringing back calculators, what do you think is going to happen when I get closer and closer to having those points basically overlap? Like these 2 points are far apart, these 2 points are closer together. These 2 points are so close together, you can't even see that they're 2 separate points unless you really, really zoom in. So how do we do this? Bring back the calculator. So bring back the calculator. Let's make you a little bit smaller. There's an easy way to evaluate functions that I need to teach, and it's hard to teach on the screen. Normally, if I had the Promethean board, I could kind of point out at the buttons that I'm using. So I am going to be using the Y equal to button in the very top left, the gray button of my calculator. When I hit that, it comes up to this menu that says, okay, here's a list of functions that you can type in. I want to type in this function. And here's how you do that. This negative symbol is to the left of the enter, not above the plus sign. The symbol above the plus sign is a minus, which is a little bit different than a negative. So I'm typing in a negative first, and then I can just type in the 4.9. So this is another thing that you probably have to learn. This T has to be entered as just a generic variable. So if you see that green alpha in the top left of your screen, a little bit to the right of that, there's the XT theta N button. That is just, in general, the variable key, and we are using an X for our equation because we have no choice. So I'm going to say X and then squared. I hit the X squared button above the log and below the X to the -1. And then I say plus 25, hit that variable key again, plus 5. So I have my equation entered, and now I need to get out of the screen. So you might see there's a quit underneath the window or to the right of the second button, but that quit is blue. In order to activate all the blue buttons, you have to hit the blue second key. So if I hit second, and now you can see it's turned red because I've hit it. And if I hit mode, it will quit out of the screen and go back to the main screen. And now I'm ready to use this formula over and over again. So essentially what I need to do is I've called this formula y1. I essentially need to say, okay, take y1 and plug in 1. So essentially what I'm doing here, I'm doing h of 1, but the way that I do it in the calculator is I'm typing y1 of 1. So to type that, and I'm gonna erase this in a sec, so you don't need to write that down. I'm going to type in y1. The way that I do that is I'm gonna hit alpha trace. So alpha is that green button on the left, it's now turned red. And then if I hit trace, which is in between zoom and graph, it will do the y variable key. And it says, okay, which y variable do you wanna use? Which function do I wanna use? I'm just gonna hit enter on my y1. It says y1. And I'm gonna start my parentheses and type in 1, close the parentheses, and you say, okay, if I plug in 1, I get 25.1. And look how fast that was to evaluate the function. I mean, I did a lot of talking, but this gets really fast when you're getting going. So you can say, I have y1. I happen to know, and I'll write it down just for now. I'm going to do it a faster way in a sec. This is 25.1. Excellent. Well, how do I plug in 1.1? And again, you hit alpha, trace, y1 of 1.1. There's an even faster way to do this that I want to talk about in a sec. So 26.571. Instead of having to go through all the menus again and hitting alpha trace, you can literally just hit second enter. If you hit second enter, it will bring back the previous line. If I hit second enter again, it'll bring back the line even before that, and you can just change in these numbers. You by default, your calculator will type over itself. The calculator that I'm using doesn't let me type over itself. I actually have to hit the delete key, and I could type in like a different value, like 1.01, and then I could calculate it that way. So that is too slow. I want to do it all in one step. So I'm going to write out a formula, and then I'm going to type in that formula, and then I can reuse that formula for A, B, C, and D. I know there's a lot of steps here, but I want to teach you guys how to use the calculator in the most efficient way. So essentially what I'm doing is I'm finding the slope. So the slope is going to be, notation-wise, I'm going to use H instead of Y. So I'm going to say it's H of 1.1 minus H of 1. That's the change of the Y coordinates, because if I have H of anything, that's the Y coordinate of that X coordinate. So, and then I'm going to divide that by the change in the X coordinates, which is the change in these two values, right? So if I do 1.1 minus 1, that is the change in X. And this is what I'm going to type into my calculator, but instead of having an H, I'm going to have a Y1, type that in, and we have to be careful because all of that needs to be in parentheses, all of that needs to be in parentheses. It won't look quite right on the calculator, but it will work, I promise. So I'm going to type in alpha trace of Y1, so I hit enter, of 1.1. Ooh, I forgot my parentheses. I remember how I said I need parentheses right here. So I need to come back over here. And this is done on purpose. You need to hit this insert key. So you can see to the right of mode, above the stat key, there's the delete key. And above that in blue text is the insert key. So I need to hit second insert. And now I can type in my parentheses. And then as soon as you move your cursor, you'll realize that the blinking cursor looks a little bit different on your calculator, which means it's gone off of the insert and it'll type over. So I have Y of 1.1, and I need to subtract, and I'm going to do alpha trace Y1 and then start my parentheses of 1. Okay, so I'm going to end the parentheses. So everything right there is just the numerator. And I have that extra set of parentheses. You'll see the parentheses right there and an extra parenthesis right there to lock in that numerator. Now I'm going to hit the divided by key, start my parentheses again because I'm about to do this denominator down here. Didn't mean to move the screen there. And I'm going to do 1.1 minus 1. Yes, you know it's just 0.1, but you can type it in, finish the parentheses, and hit enter. And we get our slope. So our slope here is going to be 14.71. So I'm curious, do we need to worry about units here? It does say indicate units of measure. So I'm glad I came back and checked. So 14.71 what? Well, let's read the question. So we have h measured in meters and t is measured in seconds. So it's going to be meters divided by seconds, and our unit is meters per second. So I'm going to write meters per second. Again, the abbreviation for meters is just M. If you need to write minutes, then the abbreviation would be minutes, but this is meters, so it's like that. Okay, so we have 14.71. I need to box my answers so that way the AP grader or the teacher can see exactly what you're looking for. And then I'm going to do the same thing again. So I'm going to write out the formula, but the way that you do it on the calculator is much faster now. So now I'm going to do h of 1.01 minus h of 1 all over 1.01 minus 1. Again, it's essentially the same formula. I'm just kind of swapping out the 1.1s for the 1.01s. So how do you do this on the calculator? You're going to hit second enter to bring back that previous line. So I have to insert. So instead of typing over myself, I have to hit second delete to insert. I'm going to type in a 0. As soon as I move my cursor, I need to do that again. So I'm going to come back all the way to the right spot, and then I'm going to hit second delete to insert, and I'm going to hit a 0 here, and I'm going to hit enter. And you can see that now my slope is a little bit different. Again, these slopes should maybe be converging to a single value. I have the slope of 15.151 meters per second, again, because same units. And then with part C, you're going to do the same thing again and change the value. So I'm going to hit second enter. Oh, maybe I should write it out before I do the calculation. So I'm going to write, this is going to be h of 1.001 now, minus the h of 1 is still minus the h of 1, all divided by 1.001 minus that 1. All right, so on my calculator, I'm going to come back over here. I'm going to hit second delete to enter a value right here. Come back over here to my 1.01, hit second delete to do the insert of a 0, and then I'm going to hit enter, and I get 15.1951. Again, why am I not rounding to 3 decimal places? Didn't you just talk about that? Yeah, but it was exact at 4 decimal places. Might as well just keep it. And again, units are meters per second. So I'm going to go ahead and box that. And then finally, we have to do this one. So now the rightmost point used to be 1.001. Now the rightmost point is 1. So I'm going to say h of that rightmost point minus h of the leftmost point, 0.999, which again is really, really, really close. Kind of like this one, it's 0.001 away from 1. And then this is all going to be divided by 1 minus that 0.999. All right, type it in the calculator. So I'm going to hit second enter, and I'm going to delete key. So I'm going to hit delete, delete, delete. It's kind of like the backspace. And it's going to be 1 minus 0.999. Then come back over here, and I need to delete this, and now I need to do second insert so I don't accidentally type over my parentheses. And I'm going to type in 0.999 there. As soon as I move my cursor, I need to insert stuff again. And I'm going to delete, 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 and I should be good now. I think that looks good. I'm just looking at it. I get 15.2049. So let me write that down. 15.2049. And that, again, is meters per second. All right, so what does all this mean? Let's get rid of that calculator so I can see the screen. So based on all of these numbers, what do we think the time or the rate of change is, that instantaneous rate of change, if I only had 1 point slope, when it actually is 1 second? Because these values are all really, really close to 1. I would say they get better and better. And then these two values are really, really, really close to the actual 1 point slope. We don't have the ability to do that because we're not in calculus. That'll be next year. What do you think it is? I mean, this value is really, really close to 15.2. This value is also really, really close to 15.2. I think it's 15.2. 15.2 meters per second. Why do I think? It doesn't ask me to say why, but the reason I think that's close is because these values should be closer than those values because they are closer to 1 point. And those two values, if I kind of take the average of them, I think the average is exactly 15.2. All right, so now it's time to actually talk about that particular point. So again, we call this the instantaneous rate of change if I have 1 point slope, and it's the rate of change at 1 point. I'm going to be calling that 1 point slope, or I can use all of this as well. We can't do that in AP Precalculus. I've already talked about that, but we can do two things. We can estimate the rate of change at a point by finding the average rate of change over that small interval. That's literally what we just did, right? We took a really, really small interval and we said, okay, that's probably the 1 point slope. The other thing that we can do is we can just estimate the rate of change at 2 different points. So we can estimate the rate of change at 2 different points by estimating individual rates of change using the concept of a tangent line. So, and we're going to be talking about a tangent line on this next page. And there's this interesting note down here that when we discuss the rates of change of a function, we are essentially discussing the slope of the graph. Yeah, so I've talked about this over and over. Rate of change is the same thing as slope. So we have positive rate of change means that we're increasing, and negative rate of change means it's decreasing. These are synonymous. These are interchangeable. So in your notes, you need to write down that these two things, switch them back and forth. Negative rate of change, decreasing. Like the definition of decreasing means negative rate of change. Or if you see a negative rate of change, that means we are decreasing. They are interchangeable. Be ready for those words to be swapped out in any sort of multiple choice question. So look at example 5. Are they positive rate of change or negative rate of change? So the way that we solve these is you look at slope. I mean, I said it over here again. It's just slope. And slope, as you might remember, is the change of y divided by the change in x. So, and it doesn't really matter which one is on top because it's just division and you're caring about positive versus negative. So look at this. Child's age. Is the child's age going up or does it go down? I mean, we're not Benjamin Button, so the child's age should be going up. So this should be a positive value. And what about the child's height? Again, no Benjamin Buttons, and we're assuming there's no weird amputees going on. The child's height should consistently be going up until they hit an adult, and then it stops and it's 0. But for a child that is not a fully developed adult, they should be increasing in their height. Notice I have a positive value and another positive value. I don't know where they go, but I know that a positive divided by a positive is a positive value. Therefore, this sort of slope should be a positive slope. That's how you have to do all of these. All right, so let's talk about a golfer's skill level. A golfer's skill level, in theory, should go up the more that they practice. So you're going to assume that the golfer's skill level is positive. I don't know why I did a circle that time. Circle is usually reserved for the final answer, in my class at least. What about a golfer's score? So is a good score something that's like 100, or is a good score like 1? In terms of a golfer's score, you want to get the ball in the hole with as few hits as possible. Each hit counts against your score. You want a low score. So if you're getting better, then in theory, your score should be going down, which means this is a negative value. We have a positive divided by a negative, which is a negative. Or I don't know, maybe it's a negative divided by a positive. It doesn't matter. I know that however I combine those two, this should be a negative slope. There are a few weird things that make you have a negative slope, like doing better sometimes is negative. One example, obviously, is a golfer score. Maybe you can do any sort of golf, like if you do disc golf, or if you do class rank is another one, right? So if you rank yourself in a class and you can say, hey, I happen to be number 1 in my class. That's the best person, which means that you have the best GPA in your entire school. So class rank and golfer score kind of are opposites. You want to get as low of a number as possible. All right, let's talk about this next one. The height of the ground of a coin dropped from the I don't know how to pronounce this, Burj Khalifa versus the speed of the coin as it falls. Okay, so I'm going to start with the speed of the coin. Speed of the coin as it falls should eventually be going up, right? It should be a positive value. It should get faster and faster and faster until it hits its maximum velocity and it stays at that speed. But we're going to assume that that never happens. It just speeds up and speeds up as a positive speed. So the height from the ground, the height was like really big, and then that height slowly gets smaller and smaller and smaller and smaller and smaller until that height is eventually 0 when it hits the ground. But our height should be going down, so that is a negative. A negative divided by a positive is a negative. All right, so estimating rates of change. So you can see here that we're eventually going to be doing this. Yeah, it says to sketch tangent lines down here. We're not going to do that until it tells us to. So we have a graph shown above, and check out this line right here. This line is what's known, and label it. Oh, I was about to label on the graph. There's a place right here to label it. This is called a tangent line. A tangent line is also known as a one-point slope line. Instead of connecting 2 points, you connect, it's just 1 point, and it seems to match that slope of that instantaneous rate of change. So there's a small little asterisk when I say like tangent line only touches the function one time. You're like, well, Mr. Sindel, if I have some sort of tangent line, I don't know, what if I do the tangent line right there, and I have this line, and it touches an infinite number of points? You're talking about just within a local range. So like if I were to zoom in and only talk about, hey, just right there in that one small radius, does it only touch one time? Yes. And then the student is usually a smart aleck. Like, okay, my tangent line goes like that. It only touches through 1 point. It should match the general slope of that line. So you can see that the slope is here, 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 here. Like the slope should match the slope of the line as it's moving through the function. So don't do something that's perpendicular or some weird angle. It should match the slope of that line. It should be nice and smooth. All right. So again, there's words down here. Slope of the tangent line, the true rate of change. We'll talk about that more in calculus. What is that rate of change? I'm going to swap that out again for the word slope. Estimate the slope when I have x is equal to -4. So check this out. Here's x is equal to -4. What is the slope of that line? I'm going to estimate it. And we don't have what are known as lattice points. We don't have things that go through the crosshairs, but this one is really, really close. I'm going to choose that point. It's kind of close to the crosshairs. And this point is also really, really close to the crosshairs, so the lattice point, which means if I go ahead and say, okay, my change in y up in this direction is, what is that, +4, and my change of x over here is a +3. That means I've gone up 4, right 3. My slope should be about 4/3, and not exactly 4/3 because again, it didn't go through this lattice point, but a good estimate is about 4/3, I would say. So I'm going to say 4/3. I like to color code that. And maybe someone else can have a different estimate of maybe it's 3/2. There's a bunch of different ways that you could estimate that. Example 7, sketch the 5 tangent lines. So this one, it's kind of hard to see. Let me go ahead and do like green or something so you can see it if I put it on the black. So that tangent line happens to be like kind of on the line. All tangent lines need to be lines and not curves, so they do need to be straight. And then try another one down here. So here's this tangent line, and then I'll have a tangent line. This one is like a slope of 0 down here. I have a tangent line right here, and I have a tangent line right there. That one can be better. Yeah, it stays on the line. It's kind of hard to see with pencil on the black pen or the black ink, I know. So those should be the tangent lines. So cool, check. Example 8, does a graph of f appear to have a greater rate of change? And again, I see that word rate of change, slope. Rate of change and slope are basically the same thing. Does the graph appear to have a greater slope at 4 or at 5? And explain. It does want us to explain now. So I'm looking at 4 and I'm looking at 5. Which of these two slopes is a larger slope, I guess? The greater of the slopes. Well, we can see that there's this concave up, which means I'm kind of pulling the plane up. I'm pulling the plane up, right? You're pulling up, which means the slope should be increasing. The slope should be increasing, which is, by the way, the definition of concave up, which means this slope should be bigger than this slope because it is after the slope in a concave up area. So you should say x equals 5 has the greater rate of change. I know you want to say slope, but we have to use the same words that were given to us. Why? Because it is on an interval that is concave up and is after, I guess, after x equals 4. If you're in an area that is concave up, generally speaking, if you're to the right of it, I don't know if I should be using the word after it. Maybe I should have used the word right. If you're to the right of a point and you're concave up, you should be a higher slope. All right. keep going. This is a long lesson. I know, guys. We got this. So these words are interchangeable. So if the rate of change is positive, then it's increased. I think didn't we already see that back before? I feel like we've seen that before. Oh yeah, right here, right? Positive rate of change is increase. What did this say? Rate of change is positive, increase. We've seen it now twice. So again, these are interchangeable. If you have a negative rate of change, a negative slope, right? All of these rate of change out for the word slope. If you have a negative rate of change, then you have something that's decreasing. If something is concave up, that means that the slope itself is changing, and it is a changing by an increasing amount. And if the slope is changing and it's decreasing, then it's concave down. These two definitions are usually harder for more students than these, because these just intuitively feel correct. These can be really tricky, because this is saying the slope is positive. This is saying the slope is changing, and it's changing by an increasing amount. So be careful. If the slope is changing and it's talking about how it's changing, it's talking about concavity. If it's talking just in general that the slope is a certain value, it is positive, and it's not talking about how that slope is changing, you're talking simply about increasing and decreasing. All right, let's see if we can apply this. The graph of f is shown above. Complete the blanks to describe. What do we got? The graph of f is, okay, so increasing versus decreasing. What's happening with the heights? Or we can talk about the slopes too. In terms of the heights are all going up. Just purely based on heights, I know that I'm increasing. I'm just going to circle because it's faster. You guys can circle as well. What about the slopes? Because the definition of increasing right here is using the word rate of change, which is slope. The slope should be positive. And indeed, if you make any of these slopes, that slope is positive, positive, positive slope, positive slope, positive slope. Every single slope on that interval is positive. That is another way that you can defend the fact that it is increasing. All right, is it concave up or concave down? Well, this one kind of, to me, looks like a rainbow, right? So if it's a rainbow, it's concave down, but that's not good enough. We now have a more formal definition of what it means to be concave down. Concave down means that my rate of change, my slope, is decreasing. You can kind of see that slope was really, really big right here and is not very big right here, which means my slope is going down from left to right. That is the definition of concave down. Okay. And now, why? AP questions love to ask why. Because what's going on with the slope? And I've already said this out loud because I've done my slope analysis. Why am I increasing? Because my slope is negative. Nope, positive. There we go. My slope right here is positive, positive, positive. My slope is always positive. Tricked you guys, right? And why am I concave down? Because my slope was really, really steep, but then the slope is not as steep because my slope is decreasing. All right, and yeah, we have from Mr. Bryan Passwater, be careful, AP tips, be careful, because you have to pay attention to the wording of each statement. Is it talking about the graph of f? Is it talking about, this is what's known as the height? Is it talking about the height, or is it talking about the rate of change of f? Is it talking about the slope? And those keywords are really, really going to make a difference. All right, I think this is the last, this is the last example that we have for today. So what's going on with this first graph? And again, it's fun to analyze it with heights, but it's not necessarily the best way. So the heights are going down, therefore my function is indeed decreasing. The graph of f is decreasing. But if it's talking about the graph itself, the graph of f, if I analyze that, am I talking about slopes or am I talking about heights? I'm talking about heights. And this one is also talking about heights. My heights are going down. I agree. They are definitely going down. But my heights in general, are they positive or are they negative? In terms of the x-axis, am I above the x-axis or am I below the x-axis? What are my heights doing? My heights are positive because I am above the x-axis. Notice the difference in this word versus this word. These words are saying the slope. Rate of change is slope. Rate of change is slope. So what's going on with the slope? And slopes all here, that's a negative slope, a negative slope, a negative slope, a negative slope. These are all negative slopes. And then what's going on with the slope change? The slopes were really, really negative, and then they're not as negative because I'm trying to pull up that plane. I'm trying to increase the slopes. I'm increasing the slopes. All right. The words are all now the same, so I can go a little bit faster. The heights I guess the heights of G are all beneath the x-axis, so the heights of G are all negative. The heights of G are all increasing. The heights are going up. They are slowly getting higher and higher, so the heights are increasing. But now what about the slopes? The slopes are all positive, 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 positive. The slopes are all positive. But what's happening with the slopes? How are the slopes changing? The slope was really steep, and then it's not so steep, which means the slope is decreasing, which means it's kind of like that person that was shot out of a can that's being affected by gravity. Gravity is pulling us down. It's pulling us down. We're concave down. All right, and again, we have our last question. The graph is above the x-axis, therefore all of the heights are positive. And then what's going on with those heights? Those heights are decreasing. So the heights are decreasing. And then what about the slope? The slope is negative, 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 negative everywhere. The slopes are all negative. And then what's happening to the change of those slopes? The slopes were basically zero, and then the slopes get steeper. It's as if gravity is pulling us down. When you're being pulled down, you are decreasing your slope. All right. That concludes the notes for topic 1.2 for AP Precalculus. I'm going to go back through all the pages so we can see all the answer key that I have just created. I might have made a mistake. If you catch a mistake, it's always extra credit in my class. And that's all we have. Thanks for watching, guys. See you later.